Greetings of the day, everyone. I am Keshav Samrat Modi, serving President at SPI CSIO Chandigarh chapter. I welcome you all. Today, we all here to celebrate the day of photonics. Today, it is the day on 1983. The General Conference of Weights and Measures adopt the value of light as 299,792.458 kilometer per second. So today we celebrate Day of Photonics, and we are celebrating it with Photonics Recent and Future Technology theme. Today with us is Dr. Pavel. Shortly he will be introduced. I like to mention you all, if you have any query, kindly put it into the chat box. After the talk, our team will ask question one by one to the speaker, and then he will answer your query. And this will be our talk. And now I request our director, Professor Ramakrishnan, to give the welcome address. Before this, I will introduce our director to you. Professor Ramakrishnan received MSc Integrated degree in physics from IIT Kanpur in 1995 and the PhD degree from Raman Research Institute, Bangalore in 2001. He worked on theoretical aspects of light propagation in random media, including temporal signatures of Anderson localization during his PhD, and was supervised by late Professor N. Kumar. After working as postdoctoral researcher with Sir John Pendry at Imperial College London, he joined IIT Kanpur as assistant professor in 2003 and became a professor in 2012. He currently works as a director at CSIO Chandigarh, and he is also a IIT Kanpur professor. His current research interests include technology applications of metamaterial and plasmonics. He has worked in area of metamaterials and plasmonic nanostructure material and has published over 115 papers in referred international journals and about 70 papers in conference and research monogram entitled Physics and Application of Negative Refractive Index Material. He received S.S. Bhatnagar Prize 2016 and Swern Jayanti Fellowship in 2012. Along with this, he have many things which he do first time, like I request our director to kindly give the welcome address.
Thank you, Keshav. That introduction was not necessarily really all the people here know me. Yeah, thank you. But let me begin by saying, today is a day of celebration. We are celebrating light, and for most of us who are here, we are doing this because we like light so much. Probably the colors, probably the various sites associated with light is what motivates us. In any case, it's important to note that optics is an enabling technology. Working with light enables you to develop technology elsewhere, and that's a matter of great importance to instrumentation engineers, where there are a lot of us here. And in this particularly, nanophotonics and metamaterials are technology in the waiting, I should say. Even though the initial work on nanophotonics, plasmonics, and started in 1998, 1999, really not sufficient number of applications have come out till date. 2000 to 2010, we could have said that it's a science of metamaterials and plasmonics. That was the decade of that. And then we had a decade of various development of techniques and maybe some technologies of metamaterials and plasmonics. But I do believe that present decade of 2020 to 2030 will be the decade of applications of metamaterial and plasmonic technologies in a widespread manner. Well, there are two problems with all these systems which are being addressed very fast. One is dissipation, which actually the light is just absorbed in your devices and you don't have much light to work with. That is something that people have been grappling with. Solutions have been coming forth. And there is the secondary issue of structuring at nanoscale over very, very large areas, which may be needed for specific applications like photovoltaic and so on. And if you look at it, for example, if you wanted to cover a solar cell with nanostructures, and then you wanted to have a kilometer square of solar cells with identical nanostructured units, the number of units that you will require are about, of the order of 10 power 18 to 10 power 20 units. These kind of numbers typically we see in astronomy, not in other sciences, but this is one science which is tending towards that. There's a difficulty of this particular thing, and it is wonderful that we have two stalwarts of nanophotonics, plasmonics, who are with us today. Pavel Belov, Professor Pavel Belov from St. Petersburg, where, of course, I have read so many of his papers, and he has just published immensely important work throughout. And the second speaker, Professor Olivier J.F. Martin, who of course, at the EPFL, he has been there for many years, 20 years now almost, and he has also done extremely important work. And not only that, he's also a very close friend of mine. So it's, in some sense, we at CSIO today count it our lucky day, and it's a day of celebration. We have two stalwarts of light who are going to talk about light to us. And with that, I welcome Professor Belov. I welcome, all the people assembled here today. We are going to have a feast now once Professor Belov starts his lecture. So welcome, Professor Belov, and I hand it over to you, Keshav.
Yes, so you are muted.
Yeah, I finished.
Hello. Thank you, sir. Thank you, Professor Ramakrishnan, for your welcome note. Now I request Dr. Umesh Tiwari, our faculty advisor, to give a brief account of our chapter activities. Sir, over to you.
All right, thank you, Keso. So, very good afternoon to all of you, respected director. Today, our chief guest and eminent speaker, Professor Pavel Belov, my head, Dr. Samir K. Mandal, our beloved Professor R.K. Sinha, our former director, who has also joined this meeting. So, as our directors very rightly said, the light is very, very important in our entire life, because the light eradicates the darkness from all the sense. So we are also calling Tamso Ma Jyotirgame. So with these words, I like to give a brief note on our activities, what we have carried out in the last 4-5 months. So we start with the light. We have organized a National Science Day celebration under the SPIE chapter. Then we have also organized the blog writing contest, which was focused on the coronavirus by warrior, inspire us. Then we have celebrated the Day of Light 2020, International Day of Light 2020, under the Jyotirmay program, and that Jyotirmay program is already registered in the UNESCO, and they have also released in their I think social media. And in this program we have our eminent speaker, Professor Ananta Ramakrishna, who is also currently our director. And after that, we have organized about 10 lectures from the eminent speakers all over the world in the area of the optics, photonics, metamaterial, nanophotonics during this pandemic. And we have also organized 3 different lectures on the theme of the Rang Tarang for the equality, diversity, and inclusion in women in optics particularly. So with this, I again thanks to all of you for joining this event, and I handing over to the Keshav.
Thank you, Dr. Tiwari, for giving short brief on our chapter activity. Now I request Dr. Samir Mondal to kindly introduce our today's speaker, Professor Belov. Dr. Samir is our HOD at Photonics Division. Over to you, sir.
Yeah, thank you, Keshav. It's my pleasure to introduce Professor Belov, the speaker of the Day of Photonics. As you know, Professor Belov is one of the very well-known scientists from Russia working in the domain of metamaterial and nanophotonics. Pavel Alexandrovich Belov, Russian physicist and now heading the International Research Center for Nanophotonics and Metamaterials, St. Petersburg. Belov graduated with honors from the Itmo University in 2000. He defended his PhD thesis twice from Itmo University in Russia in 2003 with the thesis titled Analytical Modeling of Electromagnetic Crystals, and then in Finland in 2006 at the Helsinki University of Technology with the thesis Analytical Modeling of Metamaterials and New Principle of Wavelength Imaging. In November 2010, he received Doctor of Science degree for his thesis Analytical Modeling of Electromagnetic Crystals and Left-handed Materials. Professor Belov is the author of more than 300 scientific articles in referred journals, 90 conference proceedings, and 13 book chapters. His H index is 53. His work has generated over 11,000 citations. Dr. Belov has extensive experience of working abroad. Literally, he is an international scientist, worked in Finland, South Korea, United Kingdom, and also have good industry exposure. He has worked with Nokia, Samsung Electronics, and Bosch. He is a member of the Council of Young Scientists and Specialists of the Itmo University. He is also a member of IEEE, APS, EDS, MTTS, LEOS, URSI, SPI Scientific Societies. Since October 2015, Dr. Belov has been on the board of scientific advisors at Metamaterial Technologies Inc., an international optical nanocomposites company. Dr. Pavel is a laureate of the Russian Federation President Prize in Science and Innovation for Young Scientists in 2009. The prize is awarded for outstanding contribution in the physics of metamaterials and the development of devices for transmission and processing of super resolution images. He is the winner of grants for the state support of young Russian PhD scientists in 2005 and 2009. He received IET Achievement Medal UK 2006, International Denis Gabor Award, Novofor Foundation Hungary 2003, URSI Young Scientist Award Belgium 2002. He received SPI Educational Scholarship thrice, 1999, 2000-2003, and 2 SPI visiting lecture grants, both 2009. And we had a chance to visit his lab at Itmo, and it is a world-class lab. I think we people should have a chance to visit his lab. And with this, I request Professor Pavel Belov to please deliver your lecture today.
Okay, thank you very much for the introduction. I hope you can hear me well and see my slides well. It's a really pleasure for me to give this seminar lecture today. First of all, yes, so we of course suffering everywhere in the world from this coronavirus, yeah, but right now with the internet facilities, I don't need personally to come and visit you. We can do it via internet. It's really beautiful. And hopefully very soon we will be able to do it in person. And I promise to come at a certain moment to your nice country and to your nice institution. All right, today I will be talking about all dielectric nanophotonics. And the keywords is here, all dielectric. I will explain all these details later on. So it's a kind of counterpart of plasmonics, attempt to use dielectric materials to achieve many fantastic phenomena and many good applications without using metals or using both dielectrics and metals. I'm currently in St. Petersburg in Russia. A few days ago we had snow. Temperature is about 5 degrees Celsius right now. So it should be a little bit cold as compared to India. And as you can see from this nice map, this is really far away in north direction with respect to India. We have a beautiful city here, St. Petersburg. It used to be a capital of Russian Empire. Right now, it's the second city in terms of the size in Russia. First one is Moscow, our current capital, but St. Petersburg remains to be a cultural capital of Russia, window to Europe in a sense, because Europe starts about 120 kilometers away from us. Finland, Estonia, Latvia, very, very close to us. And I'm representing Itmo University. And this is recently, I would say, it's kind of young university. It was created only 100 years ago and reasonably small. It's not Moscow State University, it's not St. Petersburg State University, but we are still 6th university in Russia, which is focused on optics and computer science. This is really our specialization, and we will be talking about photonics today, which is one of our major specializations. I would like to start also from thanks to colleagues who were contributing to research which will be presented today. At this right part of the slide, you see faces of doctors and PhD students who are working here in St. Petersburg in Itmo University in our department. And at the left side, these prominent professors from Australia, from United States, from Singapore and Germany. We were collaborating with them very actively. And most of the research I will be talking about today was done together with these colleagues, yeah? So this international collaboration which we are doing in our department, I think it's very, very important. I highly recommend to all the students also to use this opportunity right now. You can write papers together with people who are currently sitting in Australia or in US. So it's really a brilliant time. Say 30, 40 years ago, it was not really possible Yeah, it was very hard to collaborate. Right now, with flights, with internet, it's really the way how we can reach very good results. Okay, to start from, I would like to start from just the basic things, from some background, and I would like to start from resonances in nanoparticles. As all we know from basic course on optics, so basically we can distinguish two different scatterings. Say Rayleigh scatterings, then the dimensions of the particles are much, much smaller than the wavelength. Then only probably material of this particle is dictating frequency response of this particle. And Mie scattering, then dimensions of the particles are comparable with the wavelengths inside of the particle or sometimes outside. Then you can have completely different scattering. So what I will be talking today, I will be talking mainly about Mie scattering, which actually looks like Rayleigh scattering. So dimensions of nanoparticles of dielectric silicon in particular, which we will be talking today, will be much smaller than the wavelengths. But resonances will be dictated not by material properties of the particle. They will be mainly dictated by dimensions of the particle, because it's really will be like a predominantly Mie scattering. You know, from Mie theory, when you expand a scattering of spherical nanoparticles into different modes and different multiples, you can distinguish modes which are electrical. In the far field, it looks like electrical dipole, and magnetic modes, which in the far field looks like magnetic dipoles. You can distinguish them by distributions of magnetic fields and electric field in vicinity inside of this particle. And usually, say for plasmonic particles, the people are focused on electrical mode, because at low frequencies for plasmonic particles, particles made of noble metals, predominantly electrical mode is excited. But today we will be talking about possibility to have particle made of another material and have magnetic mode response. Actually, altogether with higher order multiples response, but in order to do not mix up these things, I will, in the talk today, we'll be talking only about electrical and magnetical responses. Over here, you can see that usually if you have, say, silver or gold, in particular nanoparticle, you apply electric field. Usually it will be polarized along this field and will work as electrical scatterer. You will have electrical dipole response. With Mie resonances in dielectric, you can have electric dipole together with magnetic dipole. You will have magnetic response. The field inside of the particle is circulating, and outside you have magnetic dipole. So basically you do not have magnetic materials over here, but you do have magnetic response. I think it's fantastic, because usually in optics we are dealing with electrical field and electrical response. Over here, this nice nanoparticle feature magnetic response, which is given for free to you to use, actually. The only requirement for nanoparticle to have magnetic response from electromagnetic point of view is that it should have high dielectric constant, high index of refraction, or high dielectric permittivity. The best candidate by now is actually just silicon. Silicon has dielectric permittivity around from, say, 12 to 20 in the visible domain of spectrum, with quite small level of losses. And this is most popular material right now, but also a lot of groups around the world are trying to use germanium and other materials, which you also can see this at this slide. With germanium, there is a problem of anisotropy. It's not really isotropic material. With some other materials, the indices of refraction are a little bit smaller. some of the results which I will be showing today, and most of them will be on the silicon, on the fuel, some other materials. Very interesting thing is that if you take a silicon nanoparticle and vary dimensions, vary radius of this nanoparticle, you can control optical response of this nanoparticle and scattering spectra of this nanoparticle. Take a look at this slide. Depending on the radius of the particle, you do have resonance peak at different frequencies. So basically, with silver or gold nanoparticle, you have to vary shape of the particle in order to resonate at another frequency. But if you vary dimensions, you increase it a little bit in all directions or decrease, resonance remains the same. Over here with silicon nanoparticles, it's not so. You can change size of nanoparticle and resonant frequency will change. It was first noticed by, okay, it's dielectric resonator, but the fact that it can be used for silicon nanoparticles. It was noticed around 2010 by groups in Germany and in Spain. And basically simple numerical calculations were showing that you do have in the spectrum magnetic resonance response, electric resonance response. And interestingly, then if you take a look at this response, yeah, for example, for nanoparticle with radius 50 nanometers, then you will get a nice peak in the extinction cross section at the, say, 420 nanometers wavelength. And this will be actually magnetic response, magnetic dipole. At lower frequencies, at largest wavelength, this nanoparticle feature magnetic response. And only at a little bit higher frequencies, shorter wavelengths, you have electrical response, electrical dipole. If you increase size of nanoparticle, then these resonances corresponding to magnetic and electrical dipoles shift to the right, to the lower frequencies, to larger wavelengths. And if you increase, this is for 60 nanometers, and if you increase it further to 70 nanometers, it's again shifts to the right. So basically, if you would like to operate and scatter as magnetic dipoles, say at 600 nanometers wavelengths, you have to tune radius of silicon nanoparticle to be 70 nanometers, and you will get a very strong magnetic response of this nanoparticle. It's really brilliant, but the problem remains there, how to create this silicon nanoparticle. And it's I will be talking about this a little bit later, and actually there are different methods how we can do it, yeah? But as soon as we do it, yeah, we will see that this particle will scatter differently at different frequencies. At magnetic resonance, at magnetic dipole, we will have scattering, dipolar scattering. In a sense, it's similar to electrical dipole scattering. The shape of the scattering is the same, but at the frequencies between this electrical dipole and magnetic dipole, you can have interference between electrical dipole response and magnetic dipole response. And at these frequencies, you can get so-called Kircher conditions. For example, you can excite simultaneously electric response and magnetic response of the same amplitude, either in phase, for example, at this point, if you see my mouse, hopefully you see it, or at this point, you can excite them out of phase. And in this case, the scattering of single nanoparticle will be either predominantly forward, so particle will no more scatter as a single dipole, it will scatter as a two dipole, and scattering will be directed in the forward direction. Or if the dipoles are in out of phase, it can be backward scattering. So you basically can manipulate the scattering of single nanoparticle by changing dimensions of these particles or the frequency. This is what you usually cannot do with single gold or silver nanoparticle. In reality, you should get these nanoparticles somewhere. Simplest way in the optical lab to do it, if you take a silicon substrate, launch femtosecond laser with large intensity, and after ablation, about when you will destroy a little piece of your silicon substrate, you will have a lot of nanoparticles around the hole which will be created by your femtosecond laser. And if you can pick these different nanoparticles and analyze their spectra, they will have different dimensions, they will have different sizes, and so they will resonate at different frequencies, they will have magnetic and electrical resonances at different frequencies. So take a look at this. These are pictures from the first demonstrations of this magnetic response of silicon nanoparticles in the visible domain. Two competing groups, both from Germany, they're doing this, and actually over here you can see that with increase of size of the nanoparticle, you see different colors in scattering. This corresponds to the shifts of the resonances to the lower frequencies, higher wavelength. And all this stuff is in very, very good correspondence with theoretical predictions. So everything, all the curves which I was showing to you, the previous slides are correct and they were confirmed. Of course, sometimes the quality of resonances are not that good as predicted theoretically. It usually depends on the quality of the material of the nanoparticle. We will return to this topic today at the later slides. Burning silicon substrate, it's a fantastic approach, but not really convenient way to create nanoparticles for particular applications. It's for first demonstration and for fun. If you would like to create real devices out of silicon nanoparticles, then you have to use proper fabrication facilities and proper fabrication techniques. I personally know 3 techniques which different groups around the world are using. We are using laser printing. Then you are actually melting substrate, and after that, droplet of liquid material goes to the glass substrate, and you can print like this nanoparticles. There is a chemical way of creation of nanoparticles when you synthesize silicon nanoparticle using chemicals, and there is a conventional lithography techniques with photoresist and other things. We were using and continue to use laser printing because it was one of the first techniques, and also we can control crystalline state of these nanoparticles. But with this laser printing, you can create some donor substrate. Basically, you can create some mask with lithography, and after that, launch a laser pulse, melt this mask, and melted material from the donor substrate will go to receiver substrate. At the receiver substrate, we will get very nice geometry which we need for particular applications. This way, for this laser-induced transfer or laser printing, you can create very large areas very, very accurately with very, very fine control of both dimensions of the nanoparticles, locations of the nanoparticles, and quality, I mean material of this crystalline state of these nanoparticles. Interesting thing which I mentioned is that you can vary size of nanoparticle, or of real nanoparticle. You cannot vary size because it's fixed. You can, for fixed nanoparticle, you can vary frequency and have electric or magnetic response. But still, there is a way how you can modify response of this particle, and this way lays in nonlinear phenomena of material of the silicon. basically depending on intensity of light which you are launching of your nanoparticle and intensity of light which is observed by silicon as material inside of this nanoparticle. Dielectric properties of silicon may change, and they may change dramatically because dielectric permittivity of silicon significantly depends on free carriers density. In the words of dielectric permittivity, it means that you can vary epsilon, it means that you can vary response of this nanoparticle. So what you can do, for example, you can tune the nanoparticle so that if you launch low intensity pulse on top of it, then it will scatter as material with, say, epsilon 16. But if you launch high intensity, then it will scatter as material with epsilon 18. And for 16 and 18 epsilon, this particular nanoparticle will have different scattering spectrum, different scattering diagram. And it may happen so that, for example, at low intensity, it will be purely dipolar scattering, only one of resonances, magnetic resonance will be excited in the nanoparticle. But for large intensity, you will have both electric and magnetic resonance excited, and you will have forward scattering in this case. Yeah. So this way, by changing intensity, you will be changing scattering diagram of the nanoparticle. And we actually have done this. We have created lattice of silicon nanoparticles of 2 dimensions. One set was pretty small nanoparticles. Other set of nanoparticles had larger size of nanoparticle. Over here, you can see linear properties, red curve for a little bit larger nanoparticles. You already can notice over here 2 peaks. One is electrical resonance, second is magnetic resonance. Over here, numerical simulation, you also can see this. And for small nanoparticles, you have only magnetic resonance at low frequencies. For this sample with larger nanoparticles, we have measured nonlinear reflection. And we have seen, we didn't know, we have made a simulation that reflection should significantly change because these nanoparticles with larger intensities launched on them start predominantly to scatter in the forward direction. What we've got difference about 15% between reflection from this sample for large intensities and small intensities over here. Yeah, and this happens only because of this magnetic resonance, but because at this particular frequency we also tested this green sample with small nanoparticles which are out of resonance at this 800 nanometers, and pure slab of silicon. This is green and black curves over here respectively. And you see that this magnetic resonance of nanoparticle increased this nonlinear reflection significantly, about 6 times over here as compared to non-resonant nanoparticles or just a pure silicon slab. This is one of the fantastic applications. I will show you more applications of these nanoparticles later on. But before that, I would like to wrap up a little bit, make a summary of this background. So if you take a silicon nanoparticle or any other particle with material which has large dielectric permittivity at particular frequency, you can excite magnetic resonance inside of this particle and outside respectively. And this nanoparticle may scatter backward or forward. You can manipulate the scattering of these nanoparticles by dimensions, by frequency, by intensity of light. And also you can use this property in order to create some other devices. Yeah, but in order to create other devices, you have to use some other additional material properties. You either have to use Raman scattering in the material, photoluminescence, excitons, nonlinearities, take into account heating of these nanoparticles, so on and so forth. We will be talking today about this. But before that, I would like to show you some optical elements which the people are already creating based on these structures, all dielectric structures or magnetic light, in a sense, as one of the co-authors mentioned in the first papers. First of all, with the help of these silicon nanoparticles, it's possible to create perfect thin mirrors in order to completely reflect the light with very, very thin layer. You can excite both electric and magnetic resonance, fulfill Kircher condition, and will have a perfect reflection. It has been realized, and such mirrors are better than metallic ones because they don't have losses, and also you can create them for different frequencies by demand, basically by engineering. All these nanoparticles, they scatter light at different frequencies. So you can do coloring. So depend over here, this is a sample how it looks like, but in different areas of these samples, different nanoparticles with different radiuses and or diameters are placed, yeah? And you see then you can get green color, red color, and basically you can use it for coloring without any problem. You can control also the phase of the light. As soon as you are controlling phase of the light, you can create ultra-thin holograms. And the people from Australia, our colleagues from Australian National University, they have created a real holograms out of these nice silicon metasurfaces. Also, thanks to all these nice proposals of Federico Capas and the groups who are following him, we also can do beam steering. The first works on this beam steering were done with plasmonic elements, plasmonic antennas of the metasurface. But right now, the people are nicely creating all dielectric metasurfaces for beam steering and creating already flat lenses out of it. Yeah. So this is another story. When you with very, very thin layers of metasurfaces, you can really create high aperture lenses. Yeah. And probably because you don't want to have very large losses, silicon is really good competitor over here as compared to metals. And also because you may not need not only to steer beams or focus beams, maybe you would like to create some other kind of shapes of the beams. Yeah, the people are doing face plates. Yeah, and for example, creating some optical vortices with the help of dielectric nanoparticles made of silicon and some metasurfaces out of it. This all things are possible because of this fantastic response of these nanoparticles. Other things over here which can be used, it's control of absorption. Yeah, I have mentioned that it's possible to change scattering of the single nanoparticle depending on the intensity. So basically, it's possible also to do ultra-fast optical manipulation. And over here, you can really create some analogs of, say, optical dipoles, yeah? Small dipoles which will scatter the light dependently on the intensity of light which is incident on this. I will be talking today a little bit about this, but you can control optical heating and you can do Raman thermometry, basically on response of the particle in the Raman signal. You can measure directly but remotely the temperature of nanoparticle, and this is also nice technique. And also you can do data recording. If you use phase change materials, you can record different responses of the nanoparticles in the different area of the disk and record data. Yeah, a lot of people are also doing this. Major part which of the work which is being done with all dielectric nanoparticles is associated with nano antennas. And there are cases when you place some quantum light emitters outside of these nano antennas, and then these dielectric nanoparticles or dimers of these nanoparticles are working as antennas, and it allows you to control the light. You can guide the light. You can manipulate the light in many senses with these nanoparticles. And this is also a very nice direction that the antennas made of silicon are following the trends when the metals were used for creation of the nanoantennas. Interesting thing appears when you place your scatterer inside of nanoantenna. And basically what it can be atoms or material inside of antenna. And then you can say control second or third harmonic generation easily. You can control Raman spectrum. You can control photoluminescence. In the latest slides, I will show you in details how you really can control all these three things. And over here, I just announced that with the help of plasmonics, numbers which the people can achieve are a bit smaller than the numbers which you can obtain with dielectrics. Predominantly because it's easier to work with dielectrics and losses are smaller, but also you do have this magnetic response, which I was talking about, which you do not have usually in plasmonics. Yeah, over here, all these components allows to increase numbers of all these effects significantly, and I even would say dramatically for all these applications. Okay. Let us start from second harmonic generation from single silicon nanoparticles. And actually, this is very interesting application, this second harmonic, because in spectrum of living tissue absorption, there is an optical window. And it's very nice when, if you can say, some shine infrared light and see response in the visible, then you can really detect this easily. But the problem is that, of course, the people have seen this second harmonic generation in all these materials. There are this many works with different materials like gallium arsenide and others. Problem is that with silicon, we shouldn't have second harmonic generation, because in silicon, the number which gives you generation of second harmonic, psi 2, is equal to 0. So it's a little bit useless from the beginning to increase efficiency of second harmonic generation in the silicon. But it's not really true, because the people do observe this. So second harmonic is not generated by crystalline silicon because of the symmetry of crystalline lattice. But as soon as you break this crystallinity, and you can break the crystallinity by just introducing surfaces or interfaces, then you will immediately get second harmonic generation from silicon. And this is what we see in our particles as well. First of all, we do have real surface of nanoparticle, which may generate second harmonic. But also, if the particle is not completely crystalline, then all non-crystallinity corresponds in a sense to interfaces between different crystalline small nanocrystals inside of this nanoparticle. And it will also generate second harmonic generation. So take a look. If you print nice silicon nanoparticles using technique which I was already mentioned, you launch a pulse, you ultra-fastly melt silicon. After that, the drop falls down, experience fast cooling, crystallization, and after that, it's already laying at some nice substrate. Depending on how quickly you can do it, you can control crystallinity of this nanoparticle. And if crystallinity is like this, then you see many, many nice interfaces inside of silicon nanoparticle. And second harmonic generation signal increased dramatically. Over here, you see dramatic increase as compared to just amorphous layer of silicon. And actually, second harmonic generation efficiency is quite large over here. And you see this spike over here, the peak. It's no more, no less, just a magnetic resonance of this nanoparticle. So this nice increase over here, it's because of the resonance, magnetic resonance of nanoparticle was observed experimentally, and as a result, you have increase of second harmonic generation. And of course, it's a result, this slide which I was showing to you, but in order to reach these results, it's supposed to tune properly this nanoparticle. What we were doing, we were changing the distance between transmitter in the sense of this silicon nanoparticle and receiver of this nanoparticle, donor and receiver substrates. And if distance is being varied from 5 micrometers to 56 micrometers, then during the time when the droplet goes from up to the down, you either can get completely amorphous silicon if the distance is small, black curve over here, with very, very small number of crystalline silicons inside. Or if the time allows, then you have very nice peak of crystalline silicon, so you're getting nanocrystallites inside, and you are getting already polycrystalline, nearly crystalline silicon. Take a look at the right curve over here. This is second harmonic generation. You can say also crystallinity in a sense, as function of distance between these two plates. If distance is small, you're obtaining amorphous silicon nanoparticles, and after that, when distance is increasing, you have some maxima. Over here, you have nanocrystalline particles. After that, you are getting polycrystalline particle. It's good for other applications. You can nearly get completely crystalline particle. But for this particular application of second harmonic generation, this nanocrystalline state is very nice. It has many, many, many nice interfaces which generate second harmonic. And this is optimum distance for which we were creating these nanoparticles. And as a result, observed this second harmonic generation, efficient second harmonic generation. All right. Second thing which I promised to talk about is Raman signal. Yeah. So Raman is, of course, the guy who invented this is from India, and this is I was not able to do not show this today, and we are using it in all life everywhere for analysis. You know the phenomena, and we are using this for nanothermometry. Thermal imaging, and we are just enhancing this Raman signal by Me resonance. It's how we are doing this. First of all, as soon as we see just increase of both electric and magnetic field inside of the nanoparticle, we are getting increase in Raman signal as well. Yeah, so enhancement is about 140 times at magnetic resonance, as comparing to the case when there is no magnetic resonance. And this is pretty simple because, again, particle has a resonance, so all the responses should have resonance as well because of the resonance phenomena of nanoparticle. But we decided to use it. Take a look. It's known that actually this Raman signal depends, frequency of the Raman signal, yeah, depends on the temperature of nanoparticle. So if we measure Raman signal accurately and nicely, we can directly measure temperature. So basically you can write simple formula how temperature of the nanoparticle is related to the Raman shift. And this is actually the line which gives you an idea how in experiment you can take the shift 1.2 and get a temperature that will be 360 kelvins. Yeah, and there is a certain theory around this, and we both see it experimentally, not only we, and there is a theory for this. We are just using this. And over here, I just would like to show you that we compared this Raman signal coming from basically resonances coming from silicon nanoparticles. You see this electric and magnetic resonances over here, and plasmonic nanoparticle. over here, and we observed very nice increase in the resonances, which was for us better for silicon, because we were able to tune the frequencies and intensities for this the larger, and we were able to convert this into temperature map. So actually color over here gives you a temperature, yeah, and this is nice, really nice technique, yeah, to obtain temperature. Usually you cannot put the thermometer at the nanoscale, but this is in a sense small thermometer, yeah. Outside of this thermometer you are measuring shift of the Raman spectrum, and by these indirect measurements you obtain in the temperature. Over here another a little bit simpler curve, which shows you, the blue curve shows you the temperature which is taken from silver nanoparticle, and this is a temperature taken by silicon nanoparticle. Silicon nanoparticle feature this nice resonances, electric resonance, magnetic resonance, over here even magnetic quadrupole resonance, and you see that that actually it heats up the nanoparticles more efficiently, and actually in a sense this nanoparticle also more efficiently as well, reciprocally. Based on this technique, from the far field you actually can get distribution of the temperature for different intensities of light which you shine on your nanoparticle, and you can see how the temperature is distributed, and these are different temperature maps for pair of the nanoparticles or triplet of nanoparticles. You can see that depending on intensity of light which is being shined, the frequency respectively, you can have different distributions of the temperature. And this is pretty nice. The people who are using this, trying to use this in biology, saying that it's quite prospective. We continue to think on using this in real life applications. Okay. What the people from biology also need at the nanoscale, they would like to see some spectra, Raman spectra, and just response spectra of some molecules and materials, natural, biological, for example, from native protein. And we decided that, okay, we have a resonant silicon nanoparticle, which is with very nice resonance. We can combine it all together with plasmonic substrate, increase both resonances altogether, and have a very nice cavity. It's already hybrid cavity. Hybrid, that means it includes both metal and silicon, and increase response from this protein over here, and also make a thermometry based on the previous technique which I have shown to you. And we actually have got very nice spectra of this protein, and we even have seen in the real time that something is happening with this protein. So in real time we were observing some processes inside, like molecular processes in this protein. So actually we first calculated and measured many structures, and calculated how near field is enhanced, and respectively how this structure is being heated. So we were varying different radiuses of the nanoparticle. Nearly all the time we have seen a localization of light in the gap between dielectric nanoparticle and silver substrate with quite nice intensity. And this is really the area where we were placing our bio objects, yeah, molecules of the proteins. And oops, sorry, can you still see my screen?
Yeah.
Okay, yeah, so yeah, something local has happened with my computer. Sorry for that. So you can place over here these molecules, and after that you can have you obtain a Raman signal out of these molecules with with high intensities at particular frequencies which are dictated by resonant magnetic and quadrupole resonances of these nanoparticles. Yeah, and over here you can see that this hybrid nanocavity red curve gives you a dramatic increase of Raman signal intensity as compared to just a plasmonic gold substrate. Notice that over here the black curve, it's a response Raman intensity from gold nanofilm multiplied by the number 10 to the 4th power. Yeah, so increase its 4 orders for this effect. So it's really nice because Raman signal is always weak, and it's nice if you can multiply it by 10 in the power of 4. And this is what we have seen actually. Depending on the intensity of light we are shining, the temperature of nanoparticles was different, and different molecular processes were happening there. And these molecular processes were traced through these Raman shifts. So these maxima, different maxima for different frequencies, gives you an idea what kind of molecular events are happening there. So the biologists who were helping us to understand this were pretty happy because it's really interesting technique when you're getting response nearly from, I would say, single molecule, which is placed in your nanocavity. And you can control the processes which are going there, both temperature and chemical processes. Okay, and last but not the least topic which I would like to cover today is nanoscale light source based on silicon gold nanoparticle. It continues our attempt to mix all dielectric techniques with plasmonics. So it's again hybrid nanoparticle. Then we mix silicon and gold. Okay, how we do this? Again, we are using this ablation technique. We have taken a multi-layer stack over here with both gold and silicon. We launch femtosecond laser pulse. Ablation happens, melting happens over here, and the droplet now contains both gold and silicon. And as a result, the nanoparticle itself contain in different areas of the nanocrystalline particles these two materials. They are not really going to any chemical reaction, they're just mixed. And over here, we've got extremely interesting free photon photoluminescence effect, which is extremely wide band. Yeah, take a look at these curves. As soon as you have photoluminescence, say from silicon, pure silicon film, or pure gold field, you're obtaining nearly nothing, no photoluminescence. As soon as you have nanoparticles of gold or silicon, you do have some response, but it's pretty big. But as soon as you have this hybrid silicon gold nanoparticle, you obtain very wide band photoluminescence response. It's like we call this tiny white nano lamp. Yes, so bandwidth is so wide. Yeah, and also it's extremely intense. Yeah, and it's happening because of this free photon photoluminescence together with second harmonic generation effects in this particular nanoparticle. And as a result, over here you can see video. We capture this nanoparticle and place it on top of the metal tip. This is the way how we are doing with our focused ion beam tip. Yeah, actually we are capturing it by static electricity and placing to this tip. It's very nice pick and place technique for nano manipulation of nano objects, which we are using. It allows us to place this nanoparticle on top of the tip. And after that, we were using this nanoparticle already on tip as a broadband near field optical microscope. Yeah, because photoluminescence of this nanoparticle is proportional, of course, to intensity of light. And as soon as intensity is so large, yeah, we can really go by the sample and scan this nice intensity without any problem. And efficiency of conversion is very large. And we did know, we already measured by ENSOM, the near fields of, say, pair of silicon nanodisks. But over here, we've done it with the help of this technique, with photoluminescence. And our numerical simulation and experiment show very good correspondence. And over here, you see the pictures. This is experimental pictures obtained by this nano cantilever with this hybrid nanoparticle on top of it. Yeah, and this is just theoretical calculations of the fields. Yeah, correspondence for nanoscale measurements is very good, and we are extremely happy. So this is really, I would say, new technique with the help of this photoluminescent signal to make near field scans and make these near field images. All right, so here is my last slide. So my attempt today was to show you that actually in the area of nanophotonics, the nanoscale, the people can use high contrast dielectrics, in particular silicon, and this is prospective competitor of plasmonics. As you have seen, we are friends with plasmonics, yeah, but we are still competing because we would like to make something together. For example, hybrid results using both classes of all dielectric technique and plasmonic technique. And also I was showing you some results about light, in particular light conversion efficiency for silicon nanoparticles. They are resonant, and at these resonances you have increase of second harmonic generation, you have increase of Raman signal, you have increase of photoluminescence, you have very nice, fantastic effects. And I hope that, because as far as I understand, this is a student chapter, so there are many students who are listening to me. So I hope that you also can continue to do something in this area. It's really fantastic. And all PhD students and the advisors who are doing research in this area are really fascinated by this. It's very rapidly and fastly developing area. Thank you for your attention, and I will be happy to answer your questions if there are any.
Thank you, sir. Thank you for very insightful talk. I request Preet, our chapter member, to take the question answer session.
Thank you, sir. So someone has privately asked, may I know the wavelength of laser used for Raman studies? How does the enhancement vary with the topography of dielectric nanospheres placed over gold and silver surface?
Okay, can you repeat again a little bit slower? What is the wavelengths which we are using?
The first question is, may I know the wavelength of laser used for Raman studies?
Yeah, take a look. It was 800 nanometers usually for this. For Raman, I really don't remember, but I think we have a tunable. Let us see. Okay, over here, even at the picture you see, it was 150. Well, yeah, 1050. Yeah, so 1 micron, a little bit. Yeah. For this femtosecond laser. In other cases, for Raman, it was probably 800 nanometers, but we have laser which we can vary frequency, and all these effects can appear at different frequencies. Yeah, so it's not really dictated by the frequency itself. We can tune nanoparticle to operate at particular wavelengths. Yeah, so. If you have particular laser and you don't have possibility to change the frequency, you can change dimensions of the nanoparticle and use it at your equipment if you wish.
And he asked, how does the enhancement vary with the topography of dielectric nanospheres placed over gold and silver surface?
Okay, something wrong is happening with your mic. Can you repeat again?
How does the enhancement vary with the topography of dielectric nanospheres placed over gold and silver surface?
How enhancement of this does what?
Topography of dielectric nanospheres. topography of dielectric nanoscales.
Topography. Okay. Take a look. So enhancement, you can control this. I was not focusing today on this. You can play with this quite significantly. Probably these slides show you that you can place this localization of electrical field in particular area. Over here, say it can be in between of dielectric nanoparticle and gold substrate. But for example, if you're using, say, dimers, give me some dimer over here, sometimes you can localize field in the gap over here. If you excite electrical responses for this nanoparticle, then you will have a localization of field in the gap between these two dielectric nanoparticles of electrical field. You can tune the geometry so that will be localization of magnetic fields in the gap. Or you can, for example, make localization in some other areas, for example, outside at the left, if you can see my cursor, or at the right side. So basically you can control it by geometry. You first have to simulate geometry which you're proposing, tune it, say, in CST Microwave Studio or in console, taking into account everything, substrate, environment, and other things. And by changing dimensions, you will be able to distribute this localization on demand. Yeah. So if you have particular applications, it will be possible to localize in particular area. Does it answer your question if I got it correctly?
Yes,
Okay.
the next question is, what will happen if we are coupling between a number of dielectric spheres based on scattering? Does it help with block waves?
Okay, tell me. Okay, so do you read it from chat as well? Yeah. Okay,
Yeah,
so okay, I was able to get. Yeah, I've got the chart. Yeah, what will happen if we are coupling between a number of dielectric spheres based now scattering? Does it help like Bloch waves? Take a look. Coupling is always good, and there are many works about coupling between these spheres. The people were studying pairs of spheres, triples of spheres, lines of spheres, and many other things. Yeah, and it looks like if it's periodical structure, if we're talking about Bloch waves and other things, yeah, you really have like a Bloch waves there and so on. But in addition to conventional things, you have this degree of freedom of magnetic resonance, which also influence on this, yeah? And you're already playing with dielectric spheres, which responds both like electric and magnetic resonance. And as a result, you have to take into account coupling between magnetic dipoles and electric dipoles, so on and so forth. Yeah, you can get hybridization over here. So this coupling can really strongly influence properties. As usually with any resonators, so these nanoparticles are resonators. You will have all possible resonant phenomena. For example, you have one resonator, you have another resonator, you start coupling them, you will have splitting of the lines, you will have anti-resonances and in-resonances, dark modes, and other things. All these things are appearing here, and this coupling influence this. Okay?
Okay.
Second question.
Let me read a question for you, Professor. Next question is, what do you think about ultra-high near-field enhancement by using some resonators, such as grating resonators with dielectric nanoparticles?
Okay, what I think? Take a look. Usually, okay, there are many resonators. Quality factor of resonator usually dictates what kind of enhancement you will get. But in order to have near field enhancement, you should have some nanoscale object. Yeah, so you can combine both nanoscale resonator, yeah, and for example some grating resonator. Yeah, So usually you will get some multiplication if you do it wisely. You will have kind of coupling between these two guys. And if you're talking about, say, localization, yeah, you definitely will be able to localize something with the help of, say, grating resonator or whispering gallery mode resonator. And after that, you will have additional enhancement because of the nanoparticle. The people are doing this, and the people are very, very happy about this. So you really can control and make dramatic enhancement over here. In our lab, we were not doing this. We have a lot of colleagues, friends who are doing that, and they're quite successful with this. In particular, very interesting results with very high localizations and quality factors appears if you have whispery gallery mode resonator and some nanoparticle nearby. You have very nice results. What we were doing in particular, we were using just these resonators as resonators, and their quality factor is high enough, for example, even to do lasing. Yeah, I was not showing today, but recently we have made a lasing out of single perovskite nanoparticle, and it was enough to have a quality factor of just this nanoparticle. So in a sense, maybe the quality factor and enhancement is already enough. But if you need more, please go ahead. Yeah, so it's completely right direction.
Thank you. So next question is, does we will be to create nullity with the help of couples my resonance?
I need clarification. What is nullity? Probably it's like a zeros. You mean vortices with zero field. If it is so, oh yeah, yes. If it's so, then of course, yeah. I was telling to you about coupling, about other things. You can create in the far field with say matter surfaces. You can create a mask and can create vortices of all possible numbers and kinds. Yeah, if you need particular vortice, you can create vortices in the near field. If you, for example, simulating something in CST Microwave Studio and looking at complicated fields, usually there are many vortices in vicinity of these resonance structures. Sometimes these vortices are laying inside of the nanoparticle, when it's a little bit useless. Sometimes they are laying outside of the nanoparticle, when it can be used. Yeah, depending on the distances, depending on the frequency of resonance, it's very easy to do it. Cannot say that it's easy to control these vortices, but it's possible. Yeah, it's very also good direction, I would say. There, these nanoparticles of silver can be used.
Thank you. Next is, what was actual cause of that Raman enhancement? Is it like Maxwell-Garnett configuration?
Okay, unfortunately, I don't know what is Maxwell-Garnett configuration, which you are mentioning, but I can you again repeat what's going on, but I need some just nanoparticle from the beginning. Some picture of nanoparticle, give me a moment. Okay, some fields. Okay, for example, this one. Take a look. You have nanoparticle. You launch a field, and this nanoparticle is resonator. If it's resonator, it means it can increase local field. Number in which it's increased, it's basically quality factor of this resonator. Over here, say electrical dipole or whatever, there is increase at this point many times. Over here, because it's magnetic resonance, there is increase of electric field many times. So as soon as you have Raman signal coming from silicon atom located over here, usually it cannot go with very large intensity, but right now it will be multiplied by quality factor of this resonator in the order of 4, if we are talking about final intensity. And this is, at the end of the day, the reason why you are getting enhancement of Raman signal. Unfortunately, I don't know what is Maxwell-Garnett configuration, but it's just a simple resonant enhancement when you place your whatever quantum source into resonator. I would say it's like a Purcell factor, yeah, effect, which gives you this increase.
Thank you.
And there was like a comment about Poincare patterns. Can we create Poincare pattern time me resonances for generating Poincare beams? Definitely. You can create any kind of beams. You can play with this, yeah? You have to read papers where the people are tuning particular nanoparticles to have a particular phases of the response light, and you can create a phase mask or matter surface which at the output can create nearly arbitrary distributions of field. Unfortunately, at a particular frequency, yeah, it will be not very wide band, yeah, but yes, you can. And last thing is to enhance nonlinearity using spherical shells. It's okay. It was with the question addition to this, like a grating resonator, probably, yeah, or to Raman. Yes. As soon as you have resonant phenomena, and with nanoparticle you have resonant phenomena, basically everything is increased. And nonlinearity, all kinds of nonlinearity are also increased for materials nearby, for material which is part of this resonator, yeah, for everything. So it's nice when both resonator itself is a source of some signals, like a second harmonic, third harmonic, or photoluminescence, and resonator itself. So you basically do not split this into the part. Usually you place something inside of the resonator in order to get increased phenomena. Over here, you can have all in one, everything in one, yeah? Both resonator and material in one nanoparticle.
Okay, next question is, can we take the Raman enhancement to be used in quantum computing based devices like Groover's algorithm?
Ooh, this is complicated. Okay, Raman, it's Raman. It gives you some Raman spectrum of the material. Any quantum computing things, it's quantum computing things, yeah? What I have to say that, for example, if you are trying to enhance some quantum effects, for example, you have something which is generating photons, and you would like to have, like, for example, single photon generation, and you need a resonator for this purpose, yeah? Or, for example, you would like to make condensation, yeah, of something, and you need resonator for this purpose. The people are using arrays of dielectric nanoparticles and nanocylinders for all these purposes, yeah? So for any quantum sources, doesn't matter what happens, this is a nice tiny resonator, which, or set of these resonators, as we told, we can make array of this and use also some array effects, yeah? For example, make a bound state in the continuum effect, or just any resonant, like Fabry-Perot resonances in addition. Yes, for many quantum effects you can use it, but it's not really directly quantum computing, as you're right, yeah? There are many more steps towards quantum computing after that.
Thank you. If anyone have any further query, they may write in this chat box, or if anyone directly want to ask a question, they may raise their hand, and I will unmute them, and they can ask question. Sagar Kumar, you can unmute yourself.
Yeah, hello, sir. Actually, I have a question regarding the picture, which is plotted in left side of this diagram. So in
Yeah.
this picture, the scattered field is in the direction of electric field. Is that possible, sir?
This is just distribution of electric field, so shining light from top, yeah, and this is intensity of light.
Yes, a scattered field is in the direction of electric field polarization, but as I know, the electric scattered field should be perpendicular to the polarization.
Okay, so electric field is directed like this. So you have concentration over here, and for this particular particle, electric field will be somehow directed, but this is intensity, so there is nothing about direction of field over here. Can you repeat the question? Maybe I haven't got it.
Sorry?
Maybe I haven't got the question. Yeah, can you repeat again? Yeah. So this is distribution of intensity of electric field.
Yes. My question is, the scattering direction of the nanoparticle is just same as the electric field polarization, but it should be perpendicular to the electric field polarization direction.
Okay, so take a look over here. Electric field is in plane. Okay, over here, direction of dipole, as you can see, it's along this direction, and the electric field is also directed along this direction. So for, if you're asking for electrical, like a plasmonic particle, usually response electric dipole is just directed along the same direction as electric field. In case of dielectric particles, you are obtaining magnetic resonance direction of magnetic dipole along magnetic field of the incident light, and the electric field is also along electric field. So in this sense, this is very similar. Or I was not able to understand the question. Colleagues, can you help me to understand the question? Probably.
Yes, sir. Do you want to repeat my question, sir? Hello?
Yeah.
Hello, am I audible?
Yeah.
Yeah. Sir, my question is that because it's a metal nanoparticle and you are showing the surface plasmon by the metal nanoparticle, which is by gold. So the electric field polarization of the incident field is parallel, and the scattered field by the gold nanoparticle is also in the same direction.
Okay, scattering field of this nanoparticle will be just a field of the dipole, electrical dipole oriented over here, and it will scatter both in the forward and backward directions.
Okay.
So this is very near field. Take a look. Yeah, maybe this is puzzling you. This is very, very near field. In the far field, distribution of field will be different. There will be no radiation in this direction to the left and the right. But this is near field. Maybe this puzzles you.
Okay, I got you. Thank you, sir.
Okay. There's
Thank you,
also
everyone.
a question in the chat, yeah?
Maybe you got a private.
Yeah, so basically there is a question about my contacts, yeah? So colleagues, yeah, there is this website. Actually, I can write it over here. It's called physicsifmo.io. This is a website of our department. You can come to this website, read something about department, and there is a contact information of me and colleagues. If you are interested in particular topics, we are completely open to discussions. We can help you and so on and so forth. Easiest way to reach us, send us email You're writing in email if you have some questions, doubts, or whatever you want. And I will be happy to answer your email if I can do it. If it's mainly related to some colleagues who are doing particular experiments or whatever, they will also be in contact with you. They're completely open for this. Yeah. And also, if you are reading some papers of our group, yeah, we also have a contact persons there. It's always open information. Just feel free to contact. We are always happy to answer to any questions.
Thank you, Professor. Thank you, everyone. I'd like to now thanks our speaker, Professor Dr. Pavel, for this very insightful talk. He gave the talk about why the dielectric materials are important. He gave various applications, including NA holograms and Raman signal enhancement by my resonance. It was a very fruitful talk for us, Professor. Thank you very much.
Yeah, thanks so much. It was a pleasure for me to give this talk. Yeah, thanks a lot.
Thank you. I request everyone to kindly switch on their cameras so that we can have a digital selfie with our speaker. Kindly switch on, everyone kindly switch on their camera. Okay, on count of 3. 1, 2, 3.
Yeah.
Yeah. Thank you.
Yeah, thank you.
Thanks, Professor Pavel, for accepting our invitation and sparing your valuable time to deliver this very, very nice talk. It's a fantastic talk by you. And we'll hope forward to see you in future, and we'll invite you once the pandemic is gone.
Okay, yeah, thank you. It was a pleasure, yeah, and keep some time to hear talk of Olivier Martin. Yeah, he will give.
Yes.
Okay, thank you. Bye.
Yeah, thank you then. Thank you, Professor Belov. Thank you very much.
Thank you, Professor. Professor Oliver is with us. His talk will start in 10 minutes. So everyone, you can take a break of 10 minutes. We will resume by 14:30 hours. Till Professor Oliver will deliver a talk in photonics plasmonic technology. Thank you.
Hello, Olivier.
Hello, and hello, everybody. It's a pleasure to be with you. I'm really delighted.
It's wonderful to see you again, and it's almost like being together at the same place now.
Almost, yes. Except I won't be able to sample the lovely Indian food.
Oh, that you can do when we will get you over here. Anyway.
Right, sir.
Yeah. So, Olivier, this is the new place I have moved to.
This is fantastic. I've just been browsing the website and I've been looking a little bit at the activities, but they are so numerous. It's really very, very impressive.
Yeah, thank you. Now we'll have to, of course, see how you can help us do many more things.
Well, if I can help, I'll be very happy, but I'm sure I will foremost learn a lot because there is such a diversity of activities and range of systems, which is quite mind-boggling, I must say.
Yes, there are more about 100 scientists here who work on various different things. And we have a very active program in photonics and optics as well. So when you come here, I'll be very happy to show you over several things.
I really look forward to that. We have to end this virus so we can travel again.
I know. It's maybe another year. Hopefully we will have the vaccine by then.
Yes, and hopefully it will not mutate too much in the meantime.
Yes. Professor Sinha, I see you also somewhere there, but your name has disappeared right now somewhere.
No, I am here.
Okay.
I too have visited Professor Oliver's lab. 10 years back, he has invited me. I was in the physics department, and then he took me to there. Professor Oliver,
hello.
From your side, good evening.
It's very nice.
So I gave a single-man lecture in his lab.
It's very nice, yes. I remember that was a few years back, probably 4 years ago, something like that, I think.
No, it is much earlier,
Is it?
2009, 11 years.
Okay, well, you see, it's still very fresh in my memory.
Yeah. So, in fact, he invited me to deliver a talk, taking me to your group. I'm just forgetting the name of the professor with whom I was working in the physics department. He was more on semiconductor lasers.
It was probably Nicolas Grandjean or Benoît Deveau. These have been, or Elie Capon. These are or were, because two have retired.
Yeah, so I was there for 2-3 weeks only.
Yes.
Yeah, so good talks are going on.
Yeah, I mean, Olivier, anyway, let me tell you, Professor Sinha was the previous director before I took over here.
Oh, I see. That's must be always very interesting to be able to keep both continuity and promote changes. It's a bit of a balancing act, but I think that's also where the duty and the vision can go much beyond the service term, which is very nice, very helpful as well.
Right. So it was coincidental. Both of us are from a photonics background in that sense.
That's very good. So you can keep on some similar priorities and agenda.
Yeah, I suppose so.
And at the same time, you have to cater for everybody, which is also the very nice. I always feel that if you can think sideways, this is when you get the best ideas. And probably being in this place gives you so many opportunities to think sideways. That's great.
Right. Just 1 minute.
I will also quickly grab something to drink and I will be back.
Hello, Sachin.
Hello. Hello.
हाँ सचिन, तुम्हारी आवाज जो है ना गूंज रही है।
अभी ठीक है? मैं लखनऊ में हूँ, थोड़ा सा रहता है प्रॉब्लम यहाँ। फोन से करना पड़ता है तो
हाँ, थोड़ा इको आ रहा था तुम्हारे उसमें वॉइस में।
Professor Ananta, we have, I hope they must have told you, we have a formal collaboration. I mean, some common project with Professor Pavel's group.
Yes, I think there is a collaboration, former project ongoing presently, isn't
Yeah,
it?
ongoing is also there. We had earlier, I mean, projects with his group. Who was selecting in DST, he has selected me in all the three groups. My own project. Who was that kind gentleman? So because two of them were selected when I was in DTU, but when I transferred there, then I took them both to the CSIO. And with that project only, I mean, grant and all, and one of my postdocs, we all together visited Russia and ITMO research group.
Okay.
And one of the projects which we have was recently reviewed. I mean, but Mandal had presented because I had to present. They were asking me to present, but I said no. With the title in the below CSIO is there, the project. So let the Mandal should present. So there was some review meeting of the BRICS project.
Yes, yes, yes. So I think that is going on okay. That project is going on all right. Now, of course, we are having a renewed push for more partnerships and so on across all the disciplines. These are very good for exposure for our people. It's wonderful.
Tomorrow again, I will be presenting to that AAAS, that American Association for Advancement of Science, how to make the facilities and technological support to the disabled people, those who are physically challenged. So I'm using all SIOS technology. Rather, I will be marketing that about the Divvinayan as well as the finger gesture and the head gestures mobility vehicle system, and your electronic knee and myoelectric arm. These 3-4 technologies, which so completely on behalf of the CSIR portion, I will be talking to them tomorrow about that.
Welcome back, everyone. I am Keshav. Now we have Professor Oliver with us. This talk will be same as before. First, our director, Professor Ramakrishnan, will introduce Professor Oliver. Then there will be his talk. Then after that, there will be question answer session. If you all have any question, kindly post it in chat box. Then our member Amit Pandey will read out them for Professor Oliver. Then after that, there will be conclusion of our talk. So I request our director, Professor Ramakrishnan, to kindly introduce Professor Oliver. Thank you.
Thank you, Keshav. Thank you. Thank you very much for giving me this most pleasurable opportunity to introduce a very good friend, Professor Olivier Martin. And, he is one of the foremost people in nanophotonics, nano-optics. It's our great pleasure to have him here. So if I may, sir, I would like to say that Professor Martin carried out his master's and PhD at the PFL, Swiss Federal Institute of Technology in Lausanne, where he is presently a professor. But he joined IBM Zurich Research Laboratories, where he looked at many things. And actually, I would say that one of the things he did was a precursor to what Professor John Pendry later published as the perfect lens. He had actually talked about, Olivier had talked about near field imaging right then when he was in IBM. And then, he's received a lecturer fellowship from the Swiss Science Foundation, and he spent 1.5 years at UCSD, University of California, San Diego, with Professor David R. Smith, who is one of the pioneers of experimental studies on metamaterials. And that is where actually I met him for the first time. Then he moved to ETH Zurich and became a professor of nano-optics there. And in 2003, he was appointed professor of nanophotonics and optical signal processing at EPFL and moved back to his initial hometown. Professor Martin has authored or co-authored over 250 articles, but in peer-reviewed journals, but that's not the important point. The articles are very important, and they have actually very often given completely new insights into the field. And his initial calculations on the plasmonic nanoparticles are often even today held as the gold standard for calculations, electromagnetic calculations. In 1999, he received the Latsis University Prize for contributions to the study of near-field optics and photonic bandgap structures. And in 2005, he organized a very important Latsis symposium on negative refraction. And that was actually a path breaker where he actually put together all the leading figures who were working on metamaterials, negative refraction, near-field imaging, everything. He just put them together in one place for 3 days, and I believe very important exchanges took place in that meeting, whereby the whole field consolidated to a very large extent as well. And that apart, he, of course, has continued to work and organize the NFO, participate in the NFO and various European collaborations. And this NFO 9 was organized in Engelberg, in EPFL. And in Engelberg, there was a meeting on plasmonic devices, which was also very important. So in 2016, he has received an advanced DRC grant on the utilization of plasmonic forces and designed tomorrow's nano factory. And he has a wonderful sailboat where I had the privilege of having a picnic with his family once. And any students who join his group should definitely ask him to at some time go on his sailboat. Yeah. Thank you, Olivier. We are so happy to have you here. And now we are going to have a party just listening to you.
Thank you very much, Professor Ramakrishna. This is an extremely generous introduction. Thank you. I will start sharing my presentation. And this gives me the opportunity to say how delighted I am to have this opportunity. I think it's really nice to be able to reach out like that. I briefly went onto the CSIO website, and I'm really amazed by all the technologies you are developing and utilizing. So I decided to put the emphasis of my presentation on technologies. And from the onset, I would like to say that probably we have other technologies than the one you have. And so if you see points where we could actually benefit from sharing our technologies, I will be very delighted. If we can fabricate samples, if there are things that can be developed jointly, I would be really very happy. You'll find my contact on the website, so nanophotonics.ch. And this is a view of EPFL. Unfortunately, it's not so sunny today, but it's not at all a comprehensive university. We are mainly focusing on engineering and bioengineering. And next to us, there is the University of Lausanne, which is comprehensive. But here in EPFL, it's relatively small. We have 12,000 students and mainly focusing on the different facets of engineering. If you have the opportunity to be in Switzerland, let me know. I will be, of course, delighted to welcome any of you. So to the talk, I'm going to very briefly give you a small introduction about plasmonics. So plasmonics is just the study of the optical response of nanostructures made from metal, coinage metal, like silver, for example. Well, one rarely sees a big bar. I rarely see big bar of gold or silver. I don't think I ever have. But if you look at photographs, you see that these metals are very shiny. And they are very shiny because the interaction with light is strong. But there is something very surprising that occurs when you take silver and out of bulk silver, you make nanostructures. This is an image from UCSD from the time I spent there. And you see in that case, these are typically 50 nanometer nanostructures. And they scatter light very, very well. But they have also many different colors. Some are blue, some are green, some are yellow, some are red. And around the turn of this century, actually, it was not really known why these guys were having all sorts of colors. There was this me theory, which works very well for spherical particle that tells you, okay, there is a given resonance that will occur at a specific frequency, which is determined by the permittivity of the material you're using. But why all the same material, 50 nanometer colloidal nanostructures, have different colors? This was actually not quite understood. And David Smith and Jack Mock was really an outstanding technician at UCSD. He was able to take the same image as this optical dark field microscope and look at it in the electron microscope. And there he discovered that these different particles, for example, this one that is blue, has a very nice round shape. But this one here, which is green, actually is like a pentagonal shape. And this one here, which is red, is like a triangle. Now, if you think about it, this is very, very surprising because, of course, we know that the size and the shape of a particle can influence the type of optical resonances you will have. But normally, a resonator has dimensions comparable to the wavelengths. Here we work in the visible with an average wavelength of, say, 500 nanometer. These particles are 10 times smaller, and nonetheless, their shape really matches. So this is also what got me quite fascinated by plasmonics. So the shape is very important, and the material also. I will come into that in a minute. And after this very brief introduction to plasmonics, this is the outline of the talk, which will really be focused on nanotechnologies and nanofabrication. So let me start actually with the two most widespread techniques for fabricating plasmonic nanostructures, where we want to be able to control the shape because we know that if the shape is different, we will have different plasmonic resonances. A very widespread technique is based on a lift-off. We usually work with glass substrate because we want to have a transparent substrate for doing successive optical experiments. We cover this with photoresist. Usually we put 2 layers of photoresist for the E-beam, like PMMA, for example. So you can have just 2 layers of photoresist with different densities for the 2 photoresists, such that the bottom layer, once it's being exposed and developed, is a bit more open than the top layer. We do that such that when we evaporate metal, like gold, for example, we don't have a continuous film all the way through. If we would have a continuous film, then it would be very difficult to remove the photoresist, and it would very likely damage the nanostructures. So having 2 photoresists is very important. And in the end, we do the lift-off process. Basically, we just leave the whole lot in acetone. You can do it very gently, not too much sonication, because this might destroy your structure. So you can leave it for 1 day in acetone until all this polymer, all the photoresist dissolves, and you're left with only your structure. In that process, we have used a so-called positive resist. It means that where the electron beam is illuminating, the resist is going to be modified. So we have illuminated in that region, and then in that region, when we develop, the photoresist is removed and we can evaporate the metal. There is a complementary technique which we now use more and more because it seems it gives even better results, which consists in working with a negative photoresist. A negative photoresist is such that we have again the photoresist in green, and the negative photoresist is such that when we expose with the E-beam, once we develop, the photoresist is going to stay there. In the previous case, the photoresist was going away. Here it stays, and we can use that as a mask for etching away the metal. So in that approach, we start by depositing the metal everywhere. Then we make our mask, typically HSQ as a photoresist, and then we mill away, typically with argon ion beam milling. So what do these two technologies achieve? Here you have a comparison. Always the left column is what you obtain with etching, and here the right column with liftoff. So we see that actually etching enables you to make extremely well-controlled nanostructures. Here we have what we call a dipole antenna, so two gold nanostructures with a very little gap in between. With etching, this gap can be as small as about 10 nanometer. With liftoff, on the other hand, because there is some space in the mask for the atoms to diffuse, we end up usually having rounded structures that are less controlled. We can do that for like these heptamers with 7 different nanoparticles that have a nice final resonance. We can even try to make little sausages, and you see with a very small gap in between. And this works indeed very well with this etching technique, usually better than the liftoff technique. We also see here for the heptamer, the shape is less well defined for the different particles that build this system. All this was made with gold in that specific case. So the material, of course, is very important when you do plasmonics. This plasmonic resonance depends on the permittivity of the metal. You need to have a metal that has a lot of free charges such that the light can resonantly excite the electron in the metal. And the metal of choice are gold, silver, aluminium, copper, tungsten, or also some very heavily doped semiconductor. Each metal has a different dielectric function, so each metal will work in a different range of the optical spectrum. Typically, gold, which is really I would say the gold standard, it's the most used metal in plasmonic because it's quite easy to fabricate with gold. It will have resonances more in the infrared. Copper is not so much used, it's a bit shorter wavelengths. Silver and aluminium are emerging. Silver will have a resonance in the blue, and aluminium, you can push the resonance even towards the UV. So aluminium is interesting if you want to look at nonlinear plasmonic effects, for example. And having this diversity of metals is very interesting because thanks to this diversity, we can have plasmonic effects at different parts of the spectrum. A question, of course, that arises and that has emerged over the last probably decade is, can we actually extend the range of plasmonic metals? Let's say I would like to have an effect which is not exactly at the resonance wavelengths of gold, or maybe not exactly at the resonance wavelengths of silver. Can I find a material that would be resonant in between? This could be useful for specific applications. And the answer is, well, actually, probably an interesting approach would be to use alloys. So in that specific study, we have been focusing on gold and silver alloys. And you see here the dielectric function. It is a complex dielectric function. You see that on most of the visible range, the permittivity is negative, which is a characteristic of metals. It has also an imaginary part, which of course we would prefer not to have because this imaginary part is associated with losses, but we have to live with that. We also notice in passing that silver has a smaller imaginary part than gold. So silver is more interesting in terms of plasmonic effects. And in gray, you have the permittivity of silver. These are actually, the solid lines are experimental data that we have measured here at EPFL. And in yellow, you have gold. Now, if I mix between these two, so if I make an alloy, for example, 50% gold, 50% silver, I can have a dielectric function which lies in between that of pure gold and that of pure silver. And the same is also true for the imaginary part. It is pretty much in between the two dielectric function, well, the two imaginary parts for gold and for silver. There are also models that exist. Here we've been using a model from a French group of Ryu, and we have actually a good agreement. They gave relatively simple formula for the dielectric function of an alloy, which is a mixture of two different metals. And you see the agreement is quite good. So if we want to get a bit more freedom with the material we use, it looks like a good idea to try to fabricate nanostructures with an alloy. But of course, we want to make nanostructures. We want to make things that are well defined because we know that the shape is very important because the shape is going to give the type of plasmonic resonance. And of course, the question that arises is, well, can we do that with alloy? You know, normally when you alloy two metals, then you heat them. And if you heat them, if you heat nanostructures, well, very unfortunately, they will lose their shape. You see here even some small kind of little rod fabricated in an alloy. If we heat them at the normal alloying temperature, we end up just having spherical particles. So it looks like it would be useful to have alloys, but it's going to be difficult to have alloy nanostructures. So to address this challenge, we have developed a technology for alloying gold and silver at relatively low temperature. So the idea also is that with this low temperature alloying technique, we can make alloys of any composition. Of course, if you do, say, e-beam evaporation and you want to evaporate an alloy, you could think of having a target which would be made from the alloy. This is, of course, a possibility, but it's a very expensive possibility because you probably know that these targets are very expensive. And for each composition, you would need another target with another composition. So our objective was just to make alloy starting with a target of gold and a target of silver, but then be able to do any composition in between. So the idea is to first define the composition of the alloy by defining the thickness of the material we will put. Say we put a thick layer of gold and a thin layer of silver on top, and then we alloy, and we get maybe 80% gold, 20% silver, or we can have a thin layer of gold and a thick layer of silver, and then we alloy and we have another composition, 0.2 gold and 0.8 silver. And after a lot of basically trial and errors and a lot of errors, we came up with that recipe, which is based on quite long alloying time, so 8 hours, but a very low temperature, 300 Celsius. And then in the end, it seems that it helps to have a little boost at a higher temperature, 450 Celsius, for half an hour. If we look at what we produce, and for that, I start with some nanoparticles, for example, triangle nanoparticle, and you see they're quite tiny with a size of in the order of 200 nanometer. This is before annealing, and this is after annealing. And the shape is perfectly well maintained. We can go to high aspect ratio structures like rods. And again, here in that case, 800 nanometer rods, before annealing and after annealing, they very nicely keep their shape. You can make also final resonance structures made out of these 4 bars, and they also retain the shape very well. And as a matter of fact, these are perfectly alloyed structures. For that, we needed to make thin films because it's difficult on a nanostructure to determine exactly the composition. But on thin films, we were able to do EDX analysis, and you see that we have a very good mixture of gold and silver. And if you do XPS, so you go through the thickness of your metal, you see that throughout the entire layer of metal, you have silver and gold in the correct proportion. Although, if you remember, we started here with having just a thin layer of gold at the bottom and a thick layer of silver on the top. But once it's being annealed, this has been perfectly mixed throughout the entire thickness of the material. So we were quite happy to have this achievement, and then we said, well, we should do something with that. And one of the things we have done are metasurfaces, with the idea of using different composition for the alloy to produce different optical effects. So for that, of course, there is another technological challenge, which is on the same substrate to put nanostructures which will have different composition. For example, on the same substrate, we want to have some structures that have 80% gold and other that have only 20% gold. And this requires actually doing two successive electron beam writing steps. So we start again with our photoresist, we write the E-beam, then we deposit the first metal. So for example, we deposit 20% gold thickness, 80% silver thickness. Then we redo photoresist. So we clean that away. We re-put some photoresist and we do a second E-beam. This is the tricky part because we need to align these openings very well with respect to the initial steps. So for that, we put some external marks on the substrate. Then we do a second evaporation. Because this evaporation is distinct from the previous one, we can very well change here the ratio. We can have now 80% gold and only 20% silver. Then we remove the photoresist, so like in a standard liftoff in that case. And finally, we do the low temperature annealing. And with that, we can produce on the same substrate nanostructures which have different compositions. We've not gone for very fancy shapes to start with. We've just done here little cylinders. So you see it's a very large area. You see that all these dots are quite well aligned. You might think, well, okay, they're not perfectly aligned, but if I magnify a bit, I see they are quite well aligned. You must realize these are 80 nanometer dots, that they have been written in two successive steps. First, we wrote those that were 80% 20. Then we wrote those that were 20-80%. And you see, of course, there might be a small displacement of maybe 10 nanometer, but still overall, this is very accurate. So we want to use that for doing metasurfaces. I will show you a hologram and a lens. So before doing that, maybe I would like to introduce briefly how these metasurfaces work. Because we rely again on the plasmon resonance of the nanostructure. And usually the plasmon resonance of the nanostructure, what we do is we use the strong scattered field. So we use the very strong amplitude that occurs when you choose the right resonance frequency. But when you do metasurface, actually, it's not so much that you're interested in. It's not this strong scattered field, but it's more another property which is associated with the fact that these plasmon resonances, they are like plasmonic nanostructure is like a small particle that is having a very standard mechanical resonance, if you want, electromechanical resonance. And for any resonance system, there is this interesting property that if you run the system at a frequency which is lower than the resonance frequency, then you will have that the response of the system, so this is the response of the system, is going to be in phase with the excitation of the system. If you take a spring in your hand and very slowly you move the spring up and down, when your hand moves down, the spring will move down. If you do the same experiment at a higher frequency, so you take your spring and you move your hand at a frequency which is higher than the resonance frequency of your spring, you will notice that actually the spring moves out of phase. So when your hand goes down, the spring goes up, and vice versa. When your hand goes up, the spring goes down. So what has occurred as you change the frequency from below the resonance frequency and above the resonance frequency is that there has been a phase change of the system. And the system responded in phase at low frequency, and now it responds out of phase at high frequency. Now, this is also true for the light that's going to be scattered by your small particle. If you work at low frequency and you excite your particle with light, the scattered light is going to be in phase with the excitation. If now you change the frequency, you go to a higher frequency, for example, you take blue light, which has a higher frequency than the frequency of the resonance of your particle, you will see that the scattered light is out of phase compared to the excitation light. So we see that with this plasmonic nanoparticle, not only are we able to scatter a lot of light, but we are also able to control the phase of the light scattered by the system. And controlling the phase of the light is basically the way most optical components work. A grating, which is just a periodic surface, works in such a way that for a wave that's incident, that's normal incidence, the different orders will go in different directions. So for example, the first order will go with a propagation direction which is inclined now with respect to the surface. We know that the lines of amplitude, the phase fronts of your light, they correspond to light of constant phase. So say, for example, here I have a phase phi equal to 0. The next line will have a phase of 2 pi. So just by being able to control the phase on the surface, I can create a grating. A lens works exactly in the same way. A lens will take a plane wave at normal incidence and it will focus it. So you see these two extreme rays are going to come towards the focal point of your lens, which means that on the one side you will add a phase of, say, pi, because it bends towards the right, and here on the other side you will add a phase of minus pi, so it will bend towards the other side. And more complicated systems like a hologram also work following exactly this principle. By engineering the phase in the hologram, you can create any type of object you would like. So in metasurfaces, we try to mimic this effect. This effect comes very, very simply about here in the case of a grating, because it's just associated to the periodicity of the grating. Periodicity will determine the phase that is added to the incoming light such that it is bent when it's transmitted. Here we do that by putting nanostructures on the surface. And what is usually done is to put nanostructures of different sizes. But what we propose here is to put nanostructures that have all the same size, but different compositions. So different type of alloys. And this is going to behave in a similar way to what we have here for grating. So we try to do things a little bit more complicated. This is again an example of this sample that we have made in that case of just two different alloys. And if you look at the image that it produces, it behaves like a hologram. So we have engineered the phase on the surface of this piece of glass using two different alloys to produce the phase that is required to make the EPFL logo when you look at the sample under laser illumination. You can also make a lens. So you can organize your nanoparticle in a way such that it's going to behave like a lens. And you see the lens has a very nice properties. We have here just a focus, which is in the order of 1 micron. And we keep in mind, we are working with quite short wavelengths because we work in the green with 532. So to produce the lens, we need to organize our particles basically in concentric circles with different alloys, such that we have different materials. And as a consequence, we'll have different phases that will produce this effect. Again, this is done in 2 successive steps for the lithography. First steps helps position alloyed nanostructure with one given composition, and then the next step will position the other alloy nanostructures. So I've mentioned metasurface. I would like maybe to make a very brief excursion, because I think also your mission in CSIO is to make not only nice demonstrators, but also to make real components that will work, and maybe work also in very harsh conditions. This is something which is rarely done actually in academia, because it's something very difficult and often very frustrating. So we got interested actually at this idea of, when we make metasurfaces, do we have to make them perfect? Or actually, can we have a bit of freedom as to what we can accept in terms of fabrication accuracy? Again, we now try to make a metasurface that's going to work like a grating. So it's going to redirect the incoming light with a specific angle. And we're going to do that by having structures of different sizes. So this is the way this metasurface works. To a large extent, we mimic a grating, if you want, because this looks a bit like what you would have in a grating. We have large structures and smaller, and then we start again with the next element. So we build a huge surface with that. But when we try our best, sometimes we have defects. For example, you see here, we are missing one of the elements. Or here we have one that has been slightly displaced. Or we have not done the lithography right, and our structures are much larger than what they should be. So a question is, actually, does it matter when you fabricate this system? Does it matter for the optical performance? I have a very brave PhD student, because he didn't hesitate to fabricate bad metasurfaces. So the unit cell is just a rectangle like that. It's made out of gold, and in that specific case, we've been using a lift-off process. You see the different 8 elements, which will basically discretize the phase. So as we would have on the grating, we have different phase on different location on top of the surface. So we discretize the phase. Here it's discretized with 8 levels between -pi and +pi. You can also make a simplified surface in which you discretize with only 4 levels, as you see here. So we have just 4 discrete levels for the phase, and that should still mimic quite well a grating effect. By varying here the length of this gold structure, we can vary the phase. So we have on the surface different lengths for the structure, and as a consequence, this will produce different phases for our elements. So very bravely, he fabricated broken structures. So he purposely put defect in his metasurface. He's very good at fabrication, so otherwise the structure looked really perfect. But you see here, there is the smallest element missing. Here, there is the 4th element missing, and so on and so forth. And then he measured these surfaces. So basically, what you do is you come in the microscope with a light that is incident at normal incidence, and you hope it's going to behave like a grating, which means that it's going to send some light into, say, the first order of the grating. Of course, it's not like Blaze grating that would be very efficient in doing that. So there is still quite a bit of light that is reflected back into the zero order that you see here. But if you look at the efficiency of these metasurfaces, depending which element is missing, for example, this one is when the second element is missing, so that would correspond for this sample for the 8 level and this sample for the 4 level system, you have a certain efficiency of your surface. And of course, our reference is to compare with the perfect structure, the structure that has all its elements. And we anticipated that as soon as you have a defect, as soon as something is moving, the performance should be worse. We were extremely surprised to notice that actually when one element is missing, and specifically element 3 or element 4, so these type of samples, it turns out that the structure works better, the efficiency is higher. It is still something we try to understand. It's probably related to the resonant effect in the material, but here the message is we aim always at doing the best structures, but maybe for a given optical function, this is not going to be the most efficient structure. So I think it's always important, especially when you struggle developing technologies and nanofabrication, sometimes it might be that having it not so perfect might actually improve. I'd like to spend some time now going to a actually quite fundamental question. Professor Ramakrishna mentioned metasurfaces, magnetism, all the excitement that has come related also to being able to have a magnetic response at optical frequency. And there was also quite a lot of controversy then when this all started, because if you go back to very gold standard physics book like Landau and Lifshitz, it is written that, of course, magnetism cannot exist at optical frequencies. It's impossible to have that. Actually, it turns out that, yes, you can have magnetism at optical frequency, but you can, in order to do that, you really have to tailor the distribution, the spatial distribution of your electric permittivity. And because you want to have material that have a strong interaction with light, to do that, actually plasmonic materials are a good candidate. And in that study, we actually use silver. Don't have time to talk about that, but we have developed techniques such that you can really work very well with silver, and also you can keep silver without any, it's not going to oxidize for a couple of months if you make a very simple dehydration process, which you can find described in our paper. So let's take a small U shape. This is reminiscent maybe of the split ring resonator for those who are versed into metamaterials. We have this little U-shaped element made out of silver. We illuminate it and we look at the light that is scattered. So we look at the cross-section of this system. If we look at the cross-section, we will see two distinct peaks. And these peaks actually are associated with what we call an electric dipole. So electric dipole is going to be very dominant in that system. We're also going to have around 600 relatively strong electric quadrupole. And here, this is the magnetic side of it. We can have around 1200 a nice strong magnetic signal, which is the magnetic dipole. However, this magnetic dipole is completely dominated by the electric dipole. So our idea was, but could we still make pure magnetic light? And also there, I think there has been a bit of confusion because we want to have just a magnetic dipole. Often magnetic dipole are being confused with the electric quadrupole term. So we want to really make sure we can separate them and if possible, find a situation where we would only have a very strong magnetic dipole. So to do that, we need to resort to a slightly more complicated system. So we use silver again because it has very low losses. You see here just two parallel bars. This is 100 nanometer, the bar length here. So our particles are 80 nanometer in size, and they're made out of silver. So you see it's possible to make very nice silver nanostructures. If you eliminate it from normal incidence, you're just going to have a mode in which both of them are driven together. So they're driven in phase, and the charges go like that. But if you start to come with some incidence, the light is going to hit this bar first, and then there will be a little delay until it hits the other bar. There will be some retardation. So you can reach a mode which starts to be reminiscent of a small current loop, you see, so more of a magnetic mode. And this is really controlled by the incidence of the light. If we go at 45 degree or minus 45 degree, we start to see a response which is a bit wider because we have now this additional mode that occurs. And we have a good agreement between the simulation and the experiment for that. But still, this is not quite pure magnetic mode. To see that, you can do a multiple analysis of your system. So you take the field radiated by these two little bars and you project it on vector spherical harmonics. And from vector spherical harmonics, you can get Cartesian multipoles, and you represent the strength of these different Cartesian multipoles. So here I have the dipole, the electric dipole, and we see that in that case, we have basically radiation, which is only pure electric dipole, strong. Just this mode is excited. The other modes, which are the electric quadrupole and the magnetic dipoles, are not at all excited. This is when you come at normal incidence and you drive the two particles like that, they will radiate like an electric dipole. If you come at 45 degrees, you start to excite this other mode, which we believe is a kind of magnetic, but I would really put magnetic in quote, magnetic mode. But still, if you make the decomposition of the field, the way it scatters, it does have a little tiny bit of magnetic dipole. It has also quite a significant electric quadrupole, and furthermore, it is still very much dominated by this electric dipole. So can we do better? So we don't really manage to get only this mode because we don't have enough delay between the two particles. So in order to increase the delay, what we can do is to change the size. We can now have a small one and a large one. We go back a bit to the metasurfaces where we had different elements of different lengths. They will produce different phases. So now we can engineer the retardation. And if we do that, we start to see indeed these two modes very distinctly. One could also describe that as some kind of a Fano resonance. I mean, we have basically for the individual rod just this dipolar mode, electric dipole, and then we have either an anti-bonding and a bonding mode that are now excited, and they are very well separated in terms of frequencies. So we see now these two peaks that appear, and the agreement between simulation and experiment is also quite good. But if we make again the analysis of this system, we have now a very nice, strong magnetic dipole. We've been able to get completely rid of the electric dipole, which had been the dominant term. We see here in the response at this specific wavelength of 680 nanometer, we don't have any electric dipole anymore, so we're quite happy. But we still have the electric quadrupole here in green, which is this term here. So this is not quite pure magnetic light. one could describe that, because often there is this confusion that an electric quadrupole is like a magnetic dipole, but it's not the case. And I hope I can show you what the difference is. Actually, at this specific wavelengths, and we see it again here, we have these two modes. We've got rid of the electric dipole, but we still have the magnetic dipole, which is strong, but the electric quadrupole, which is not negligible. And these two modes are degenerate. And this is actually our problem. These two modes are degenerate. We can follow now the current loop. This is the mode we are after. A current loop, this is the magnetic dipole. Whereas this one, which is more two sources and two sinks, this is the electric quadrupole. So they all look kind of like loop of current, but you see they are quite different. So the final step was to try to distinguish between these two modes, and this can be done in another system, a slightly different system, in which we split each bar into two. So now we have again a system with 4 bars, and we see that this magnetic mode, which we are looking for, is going to be excited by transverse electric polarization. So the electric field is oscillating like that, and as a consequence, once it has moved a bit, so once retardation has taken place, it moves in the opposite direction. So this will excite this loop. Whereas this one, so the electric quadrupole, is going to be excited just by the other polarization, where the electric field is now pointing towards each other. So we did the experiment. We fabricated the structure again made out of silver. We have again very good agreement for the response between the simulation and the experiment. And then if you make the mode analysis, you see that at this specific wavelength, you can have only a magnetic dipole. I say only, it's true, there is still a little tiny bit, that's the blue curve here, of electric dipole. You see it here, but it's very faint. And really what is dominating is the magnetic mode. So we can have just a pure magnetic mode in that system. And if you cover a surface of this with this type of geometry, and you look at it in microscope and you go into the Fourier plane, you see something that does radiate here with this perfect symmetry. So this is really the signature of magnetic dipole mode. In the experiment, you get some light reflected here, so you have to block this part. But you see here, you have something that's perfectly circular, which corresponds exactly to the magnetic dipole. And again, the agreement is very good with the simulation. So it's possible to have pure magnetic light, and it's possible to control it with the polarization. We have just seen the results for the transverse electric, which is going to drive a current through these 4 particles. If now I take the transverse magnetic, it's not the case anymore. Now what becomes the dominant term is the electric quadrupole in the system. Let me finish with some very recent results on another technology that we have developed, which is on hybrid structures. And I think there is probably a lot of interesting things to be done, although you will see that right now the results and the performance is slightly disappointing. So we've been just talking about mode, dipole, quadrupole, and so on and so forth. If we look at a plasmonic structure, a very simple, just one particle plasmonic nanostructure, it will mainly radiate like an electric dipole. If, on the other hand, we look at a dielectric structure, and I think you had quite a lot of very exciting elements from the previous talk about dielectric structures, you can have other modes like higher order multipoles that can radiate. But that's interesting. You know, it's a bit like when you play Scrabble. If you want to play just with a few letters, you can only make a very limited number of words. If you can play with many more letters, many different letters, then you can make more complicated words. So the question is, could we benefit from combining plasmonic material and dielectric material such that we can use more modes from those systems? And we have tried to do that by fabricating this structure, which is a combination of a dielectric cylinder. We want to have strong dielectric response, so we use silicon, which has a very high refractive index. And on top of that, we have an aluminum disc. So the disc of aluminum is going to be the plasmonic structure. And in between, we want to control the coupling between the two with a small spacer, which is made out of SiO2. We want to use that for sensing, so we make large area substrate with those structure. And you see here in the SCM image, you have about 240 nanometer of silicon, little bit of glass, SiO2, and on top of that, you have the aluminum disc. The technology is also quite interesting. It combines a little bit lift-off and etching. We start with our substrate. We need, for a subsequent step that I will explain at the very end, we need to have a blocking layer. So we put alumina, Al2O3, using atomic layer deposition. Then we put the silicon that we will need. Then we put the glass, SiO2, that we will need, that will build the structure. And on top, we put our two photoresists for doing a lift-off. So we do E-beam on that structure. We obtain an opening in the photoresist. And then it's just a standard lift-off procedure. We evaporate here aluminum. And then we dissolve everything into acetone to remove the photoresist. And then we're left with a structure where we have a disk of aluminum on top, and beneath we have the glass and the silicon. So we use this aluminum disk for etching away. So in that case, we use reactive ion etching, and we etch away basically we define the cylindrical structure by etching away the glass and the silicon underneath. So this provides us with the structure you have just seen. Now, in terms of plasmonics, in terms of mode, it's interesting to try to see what kind of resonances we can have. If we look separately to each individual part, for the aluminum disc, we mainly have a large electric dipole resonance. And for the silicon cylinder, there we have quite a lot of resonances that occur. We see also appearing quadrupole modes. We still have dipolar mode that occur, but we also have magnetic quadrupole that appear and quite a strong magnetic dipole that occurs here in this structure. I mean, this is well known that these dielectric resonators have all these modes. Now, if we combine the structure, we basically have kind of hybridization of all these modes, and we have a lot of different features that appear, but we see here these different prominent specific features can be used for doing some sensing. And these different structures, these different peaks, spectral features, they come from basically the hybridization of the different modes in the disk and in the cylinder. So we've put that to the test for sensing. You see here, this is done with FTIR microscope, where we put our sample and then we just change the refractive index of the material. We just did a very simple glucose measurement. We see that the different features, which we see, spectral features, which we identify with spots of different colors, they move as we change the background refractive index. And this is basically the basics of this plasmonic sensing that is done quite routinely. You determine the sensitivity of your system by determining or measuring by how much the feature moves when you change the background refractive index. So you end up having a sensitivity which is given in nanometers, so the amount of wavelengths that shifts by change of the refractive index of the background. Of course, you change the refractive index with very modest value, and you go, for example, from air to water, so from 1 to 133, and then you add some glucose, so you can go all the way to 144. So what we obtain for each feature has a different sensitivity, but the best one we obtain has a sensitivity of 200 nanometer by refractive index unit. So those of you who are versed in sensing, they will immediately realize that this is not great, because normally if you do pure plasmonic sensing, you have a sensitivity, experimental sensitivity, which is in the order of 600 nanometer by refractive index unit. So it's not so good. If you do pure dielectric sensing, although here this is really based on highly resonant cavities like waveguide and ring resonator, you reach about 300 nanometer by refractive index unit. So this is quite disappointing, because the technology was quite complicated, but that's just what we get experimentally. That's the way it works. We thought, well, maybe these results are not so good because the analyte is not interacting a lot with the strong field produced by the structure. You see here the silicon disk, the aluminum disk, here the spacer made out of glass, and we see that most of the strong optical field is inside the glass. So if we have the analyte outside, it's not going to interact a lot. One step Deb Data proposed, which I think is very clever, is to favor the interaction with the analyte. And for that, she made an additional etching step. So in order to etch the SiO2 spacer, you can find a liquid, it's in gas form, it's HF gas form, that is going to etch just here this glass. And maybe you remember when I started this part of the presentation, I said on the bottom we put a thin layer of alumina, Al2O3. This is because that will protect our substrate, which is also made out of glass, from being etched at this step. The technology is quite sophisticated, but it works. And you can produce this undercut that you see here. In the image, she has colored. So this is the silicon. Of course, etching produce relatively rough structures, but nonetheless, they have obviously nice optical resonances. This is the part of glass that has been etched. So you see it's recessed compared to the silicon, and it's recessed compared to the aluminum. The aluminum on top is obviously quite grainy. This is one of the features you cannot avoid too much with aluminum. It should not matter too much because the graininess is, I would say, a vertical graininess, and the electric field is mainly horizontal. So this should not matter too much. This additional etching step helps a little bit. It improves by about 40 nanometer by refractive index unit. So we end up having overall our best sensitivity is 245, which is not as good as standard plasmonic system, but it's an interesting technology, and this was our first trial, so possibly one could do better, and I hope some others will take up on that challenge. So this brings me to the end of my talk. I was trying to share with you some of the nanofabrication techniques we have developed. To start with, conventional e-beam lithography can be used with positive or negative photoresist, with liftoff, or with etching. And we see that etching allows you to make very, very well controlled, very small features. Then we try to expand the realm of materials we can use, and alloy appear to be interesting, and it's possible to make nanostructures that are well controlled, that keep their shape in alloys, and with that to make meta-holograms or meta-lenses. Although one spends a lot of time trying to make the perfect fabrication, maybe sometimes it's not necessary. Maybe some structures that had mishap work better than the perfect structure. So I think it's always important to try to reflect on what you are trying to achieve. And by engineering nanostructures that will remove degeneracy between different types of modes, it's possible to produce light scattering which is purely magnetic. And this is what we observed in that system of 4 bars. And finally, I think there is probably quite some promises for developing hybrid structures, so structures that combine both dielectric material and plasmonic materials. Of course, all that would not be possible without the fantastic team I have. I must say right now we are actually a bit less numerous, but I still would like to point Debdata, who's been developing our technology together with Christian, and Xiangshu, who's working on our metasurface, and Karim and Gabriel, who are working on the theory of our system. And I would really like to thank you all for listening. I'm really delighted to have this opportunity. Hopefully there will be a few questions now, but if you have afterthoughts, don't hesitate to contact me, and this is the website. Thank you very much.
Thank you, Professor. This is a very interesting talk. Now I request Amit to kindly take the question answer session.
Thank you, sir.
Amit.
Hello. Thank you, sir, for interesting talk.
Amit, little louder.
Yeah, so Amit is having some problem, I think, for the connectivity. So if it's possible, so you can take the questions.
So should I take the question?
Okay, I will read a question for you, Professor.
Okay.
So, question: can we achieve broadband flat lens transmission using a sphere array? Hello?
Yes, so
okay.
I'm trying to get, so as you see, these, did you see the slide, the screen again? Yes?
Yeah.
Okay, so unfortunately, all these materials are dispersive, so their response is going to depend very much on the frequency at which you work. And as a consequence, it's very difficult to get broadband response, especially with plasmonic materials. So it will be quite selective. You may get a bandwidth of about 100 nanometer where you can have the effect, but beyond it's very hard. And I think this is probably where hybrid materials, because the dielectric are much less dispersive than metals, so hybrid might be interesting to extend the bandwidth of this type of effects.
Okay, thank you. Next question is, what is the minimum feature size of nanostructures or gap between the nanostructures that can be achieved by ion milling?
So I would say if it's difficult to give an answer, so I'll try to give you a honest answer. You can be lucky and you can do maybe 5 nanometer. But if you want to have something which is really reproducible, as we see it here, I think you can be reproducible down to 10 nanometer. This is possible. And that's more difficult to do with liftoff. So I think 10 nanometer, you can do that. You may have to optimize a little bit your etching recipe to start with. But once you've done that, normally you would have something that is quite reliable. And I would say 10 nanometer. Once you try a bit, this is what you can get. you also see here a difference between, here we are really doing ion etching, and you see that the structures, they are quite smooth. So it's a pure mechanical etching principle. If I go to the final structures, the one we have fabricated with the undercut, you see the surface is really not as smooth. And this is because here we use reactive ion etching. So you cannot use reactive ion etching for gold. As far as I know, there are no reactive etching that exists for gold. So if you do just normal ion milling, I think you get quite smooth edges, and you can define very tiny features. And I would say 10 nanometer is what you can get. If you don't want to optimize a lot and just do it brute force, probably the first trial you will do could easily give you 20, 30 nanometer. And if you optimize a bit, you will go to 10 nanometer, I would say.
Okay, thank you. I have a follow-up question on that. You show the two longitudinal placed bar showing magnitude in optical frequency.
Yes.
So, what is the impact of this separation between those bars? And I guess those two bars are not same in size. One is a little bit longer than other. So, what is the impact of that?
So you have a very interesting point. We started with two parallel bars which have exactly the same size. They were 80 nanometer. If they have the same length, it means they have the resonance frequency exactly at the same frequency. If we make a long one and a shorter one, as is the case here, so one is a bit shorter, 70 nanometer, the other one is a bit longer, 90 nanometer, what we do is we shift the resonance frequency. So if I go back to my, I don't know, that would be maybe here. If I go back to this diagram, one structure will be resonant here, and the phase will be like that. But the other one could be, let me maybe draw it there. The other one could be resonant here at this frequency, and then you will have the phase change like that. So you see, if you work now at the frequency in between, say you work at this frequency, for one structure, you will be in phase. For the other structure, you will be out of phase. So by having different structures, you can basically engineer the response of the system at the frequency at which you work, at the frequency of the laser you use to do your measurement. Does that answer your question?
Okay, so by introducing asymmetry, so are we exciting phenoresonance here?
So you can indeed look at this in this schematic here. We see two peaks. We see two peaks because originally we had two different modes, and they have hybridized together. One has higher energy, the other one has a lower energy, and in between there is a little gap. So you can very well describe this as a phanoresonance, yes. But I would say in terms of phanoresonance, we studied phanoresonance a lot some years back. I think you must be careful that this diagram, it's a phanoresonance in what I would call the strong coupling regime, where really you split the two resonances and you have a significant energy difference between them. And in terms of phanoresonance, I think that's not the most interesting regime. We have a paper in which we studied what we call critical coupling. And I think critical coupling is much more interesting than this strong coupling here. But you're perfectly right. Most papers that refer to phanoresonance, they will go in the strong coupling. And in terms of near field enhancement, this is not the strongest regime. But you're right, this is indeed a Fano resonance.
Thank you. Another question, the distance between L1 and L2, what is the impact of that on magnetism? Does changing the separation have any impact?
So yes, but it's not sufficient. So it's a very interesting point, what this question, because as a matter of fact, you would like to have retardation. So you would like to have a large spacing between the two particles. Like this, the wave comes here and then it travels a bit further. So there is a large separation. So the retardation, in other way, the phase that the wave has acquired until it reaches that second particle is large. So that's what we like. But at the same time, if we put both particles very far apart, then the coupling is going to decrease very rapidly. And we are here dealing with near-field coupling, which strength goes with the 6 power inverse of the distance. So you have to compromise. You have to be close enough such that they couple, because if you're not close enough, this hybridization will not occur. And if they are too close, then there will be not enough retardation between them. They will just behave as a single particle. So it's really a very subtle balance that you have to identify.
Okay, thank you. So next question from chat. Maybe may it be possible to have a magnetic nonlinearity using hybrid meta-surfacing such that we may beam steer or shaping with the help of them?
So I think this hybrid meta-surface or hybrid nanostructure business is now hopefully going to emerge and take off. The very first papers on that were actually from the group of Keith Shah, who has indeed studied nonlinear effects in this system, with the idea of using indeed some of the magnetic resonance that you have in the dielectric particle to reach other type of nonlinearities. So I think this is a very good point, and as a matter of fact, probably we can use that to promote a nonlinear effect in those systems. It's something we've not really done, but I think it would certainly be a very worthy line of research.
Okay, thank you. Next question is, what material can be a good mask for argon ion milling?
So aluminium works really very well. So you see in those structures, okay, we have then done the under etch afterwards in HF to remove part of the glass. But the structure, they have been etched using the aluminium as a mask. So that's the trick here. This aluminium disc, we need it not only to define the structure, but we want to keep it afterwards because this is going to be our plasmonic structure. So aluminium works very well. It's very hard. Some structures we are doing right now, we just use the photoresist itself. So if I go back to the beginning of my presentation here, so this is ion milling. We use the photoresist, which is a negative photoresist. For that, we use HSQ, which is also a very precise photoresist. So you can really define these features very well. And it is basically like glass. And actually, it's so hard that at the end of the process, it's very difficult to remove. So HSQ would be also another material that you can use, and it's not too disturbing for optical properties because it's really like glass. It has pretty much the same refractive index as glass. So that's another possibility, aluminium, HSQ, and there are probably others, but we have not tried them.
Okay. Thank you. Next is, can we induce magnetic chirality by virtue of these surfaces?
This is an interesting question. I'm not sure I know what magnetic chirality would be. So chirality for the magnetic field, possibly. I mean, chirality is a fascinating topic. My understanding is that it's also a very complicated topic because usually chirality and chiral effects are very weak. So it could well be that one could, but I must say I've not given further thoughts to that. But that's certainly a very interesting idea, and you should pursue it. Yeah, I think chirality has a lot of potential, especially in terms of sensing. Because if you look at biomolecules, they are usually chiral, and the handedness, whether they are left or right, determines their function. And this is certainly one of the holy grail to be able to enhance chirality. Now, about magnetic chirality, I must say I've not really thought about it, so I don't know, but possibly, yes. Hopefully this type of simple system we study could give ideas for doing more sophisticated geometries by others.
Okay. Thank you. If anyone have further queries, they may raise their hand.
I just want to
so
ask.
that we can directly ask question.
Yeah, Keshav, I just wanted to comment on this magnetic chirality. Usually, that is reciprocal. Usually, chirality is reciprocal. You know, it comes by a coupling through the magnetic and electric fields. It's a diagonal coupling. So you cannot have magnetic chirality without electric chirality in some sense.
So it's the off-diagonal terms that you are saying, Ananta. Yes, that's a good point.
No, these are diagonal. The chirality is diagonal. So if you write down the constitutive relations, D is epsilon E plus a chirality times H. And similarly, B is some chirality constant times E plus mu B. And chirality coefficients are complex conjugates of each other.
Yes, you're right. Yes.
So these are diagonal. If they were off diagonal, they would be bianisotropic.
Yes, that's I mistook that with bianisotropic and magneto-optical effect. Yes, you're right.
Yes.
Yeah.
So the magnetic chirality will automatically imply electric chirality as well.
Yeah.
I mean, one cannot have one without the other. Yeah.
Yes,
Thank you, sir. Yes, sir.
So,
Hello?
is there any more question?
Yes.
So, Professor Oliver, I have one small query.
Yeah.
Do you have any kind of biosensing also using the hybrid meta surfaces because you have shown for the RI sensing? Is it possible to do some biosensing?
So I have a very gifted colleague here at EPFL who is Atice Altug, and she's really focusing on biosensing. And it's with her that we have done this measurement. So she has all this FTIR set up for that. That's basically what we've done there. We have done some electrochemistry sensing. I had a very good Indian postdoc. He's now moved to London, but he did some electrochemistry sensing based on that. And we have a couple of papers on this. So trying to enhance the sensitivity for electrochemical sensors, yes, based on plasmonic nanostructures.
And in which wavelength range?
So this was electrochemistry. So basically, there was no light. We just used the metal feature of the plasmonic.
Okay. All right. Thank you.
Not at all.
Thank you. If anyone have any further query, they may unmute themselves. Okay. So look like every query get answered. So I thank you, Professor, for your talk. I request everyone to kindly switch on their camera so that we can have a digital selfie with our speaker. Okay, on count 3. 1, 2, 3. Thank you, everyone. Now I request Professor Dr. Umesh Tiwari to give formal vote of thanks and closing remarks.
A very good evening to all. It is my honor and privilege to propose a formal vote of thanks on this memorable occasion, where we have a very interesting 2 talks by eminent professors on the niche area of nanophotonics and metamaterial. So first of all, I thanks Professor Olivier, who has spared his valuable time despite of his busy schedule to share his expertise and deliver the talk on the plasmonics technologies, and he has given a new insights in the meta surfaces for various applications. So thank you very much, sir, for accepting our invitation and sparing your valuable time with us. I also thanks our worthy director, Professor S. Ananta Ramakrishnan, for his guidance and support for organizing this event on the day of photonics. I also thanks our former director, Professor R.K. Sinha, for joining this event. My heartfelt thanks to all the attendees, particularly I thanks to Keshav Samrat Modi, the president of SPI CSIO chapter, for making this event successful, and all the other office bearer of the SPI student chapter of CSIO for their help and support on to organizing this event. So once again, I thanks all and say a good day and goodbye to all of you. Thank you very much.
Thank you, sir, for your kind word. Thank you, Professor Oliver. Thank you, Professor Ramakrishnan. Thank you, Dr. Tiwari. Thank you, everyone, for sparing your time and attending our event. I am also thankful for to our SPI chapter members. Without them, this event cannot be possible. Thank you, everyone. This meeting is concluded. Thank you.
Thank you, Keshav.
And
Olivier, just before you log off, I wanted to ask you one thing.
Of course.
Is Professor Herzig still with you in EPFL?
He has retired 2 years ago.
Oh, okay.